Hi everyone. So in this demonstration, we'll look at one of the most powerful machine learning algorithms called Bayes, right? And it's a probabilistic method based on something that we know named Bayes theorem, right? And that's how the kind of name came in here. So we're going to go through some basics of machine learning, the various types of machine learning algorithms, and with that context, we will slowly get into a demonstration where we will see the working of Bayes. Right? Let's start. Right, so this is the broad kind of an objective which I'll be going to cover. I'll talk something about a bit very crisp details on machine learning. I'll introduce to the kind of classification problems which we can solve using machine learning techniques, some of the algorithms which are used for classification problem solving, and then we'll with that context set we'll discuss the Bayes with some use cases and finally a demonstration in R. Okay. So what is machine learning? So as like in many of the use cases across industries in different context and in different business setting, people have been finding scenarios and problem statements where human beings are kind of slowly being replaced by decisions taken by some intelligent system. So in all of these use cases, the common thing that comes out very clearly is it is very difficult to design a software system which can be coded with a rule, right? Or maybe plenty of rules. So in traditional system of designing a software and like coming out with a completely automated processes, the algorithms that goes behind designing such softwares had a very clear logic or algorithm which is like following a sequence of steps. And in these sequence of steps, all these algorithms have a predefined nature. That means you code a particular logic and that logic is executed by the algorithm and hence the software works on that. But with the problem statements, which was like hard to do this way. For instance, if you want to design a system for speech recognition, right? Speech as a specific data point is quite different from one person to the other, right? So it's very difficult to set a rule-based or a logic-based algorithm which can recognize a particular speech irrespective of who is speaking that word or speaking that sentence. So it's very difficult to design such an algorithm by just mean of a logic or a procedure. So there comes the aspect where we need to learn certain aspects or certain features of the voice that is given as an input to this speech recognition system. And these are the sort of typical examples where the machine learning algorithms really started to play a big role. Similar is the case with, let's say, face recognition. Everybody is different in terms of the appearances. So it's very difficult to do a hard coding or define a logic that this is how a face looks like. So you need to design an intelligent system which can like iterate through hundreds of thousands of images of the face and then start to form a pattern out of it. And that patterns is what goes behind any learning system, right? So I'm going to discuss certain aspects of this and how to design such a learning system. And if you're able to successfully do that, a lot of problems which had something very similar in this kind of scope can then slowly be made a bit more intelligent rather than new hard coding things on it, right? And that is where this paradigm shift is happening in industry as well. You are moving from a more procedural or stepwise algorithmic way of creating softwares to machine learning by itself and then taking these sort of calls and building a program based on that. So that's how your softwares and products are moving in the next gen to come, right? So having said that, machines are trying to learn these faces and the kind of voice data, it is also possible that there is a certain amount of error in doing so, right? Because we are not giving any hard-coded rule, which we know that it's definitely going to work. Like for instance, if I want to give you an example here, what Google does a page ranking algorithm, right? And that algorithm is about a predefined steps. You give a set of data points to this algorithm, it comes out with a score for a web page. And based on that score, if a web page has a very good page rank, it comes at the top of your search result. So which is a very procedural way of doing it because Google has cracked that algorithm, right? But it is not so possible with all the different sort of problems, which is a bit more complex than a page ranks idea. right? And that's where machine learnings are like slowly taking over the use cases. But if let's say Google would have gone the other way of building a machine learning algorithm rather than building a procedural or heuristic based page ranking algorithm, it would also have faced lot of errors. And in that process, it might be possible that you might start to get a lot of irrelevant web pages for the search query you are doing. And that's the only reason Google at till this point have not extensively changed page ranking algorithm to work like a machine learning procedural way, right? So keeping both of these things in mind, that there are problems which are very hard for a heuristic algorithm to solve, and at the same time there needs to be given an effort where such a heuristic algorithm is possible for the problem statement. So if you are able to evaluate on these two aspects, then you know that for a given problem whether you want to go the machine learning way or you want to go to the heuristic way. And giants like Amazon and Google and Facebook of the world have like mastered the skill of identifying the problem and which way like we should be moving, right? Having said that, it's not so easy. It comes with a lot of experience and working on many problems, right? So with that context, speaking of the details, here the supervised and unsupervised learning is the two major kinds of learning algorithms, right? Which in its own nuances has a lot of details internally. So I'm going to talk about a supervised form of learning today with taking the naive Bayes as an example, right? So I'm going to elaborate anyway on this in detail. Okay. So one of the problem types that supervised learning solves for us is classification, right? Given a record, can I like classify it into different categories? So for example, if it is fraud detection in a banking system, a fraud transaction detection in a banking system, whether a given transaction is fraud or the genuine, right? Or if I'm like trying to understand if it is going to rain tomorrow or not, again a binary classification, yes or no, right? Or if I want to understand given a set of files, if that file is a malware, and if yes, that's a binary problem to identify whether it's a malware or not, a binary classification problem rather. And if I want to go one step further and say which type of malware, is it a Trojan, it's a virus, or it's a worm, and so on, right? So then this becomes a multi-class problem. So in classification, we are all like interested in knowing which class the data belongs to or which category the data belongs to. Obviously, there is going to be a learning involved here from the past data that we have got, right? So there are many classification algorithms. The one which we are going to focus today is naive Bayes. All right. All right. So starting directly on what naive Bayes is all about. Let's take a very small fun example here, and then basis that we can able to like understand this algorithm much better. So let's assume here that like you are a really great football enthusiast, and most of the time when you like go to play with your friends, it suddenly starts to rain, and maybe there are like other weather condition. It's like very strong wind, or things like it's too hot outside, as in the weather. And there are many other factors also which could be possible. And because of these reasons, you sometimes go to the field, but like end up disappointed, like because of these weather conditions you could not play. So is it like some way possible that by feeding an algorithm some set of information about your weather condition as such, you can maybe come out with a prediction whether we should play today or not, right? Like very cool algorithm which you like can show to your friends and be like the geeky person and a footballer, right? So these are the possible weather combinations which we can normally get. We can have maybe in summer, we can have like in summer too hot extreme weather versus a warm kind of cool weather. In monsoon, it might be a light drizzle versus strong rain. Similar in winters also, there might be possibilities of winds and so on. So a combination of weather conditions. In the summer, monsoon and winters, we can have conditions like too hot, like normal, versus too windy versus no wind, right? So let's say how we can model this approach and try to come out with certain predictions. So good thing is the fellow football enthusiast as well as who understand machine learning and all the ideas behind it has created a good data set from his past experiences, right? And that data set has a lot of information in it. We're going to get to the dataset discussion in a while, but let's see what kind of cases we can normally get. In the dataset which is being collected, we see that there can be like different scenarios based on that, and these are the typical sort of those scenarios. So let's say we are in the summer and the temperature is like sunny outside, right? Which means the temperature has certain high value. So let's assume for now that it's more than 40 degrees Celsius outside, right? If that's the case, it says these circle represents the sort of probabilities associated with it. So in how many instances, like in the past, did we had a really hot weather and we played football as well? So your friend has collected this data, and he says that there were very few instances like that. So that's why the probability is marked by the small circle, and which is like quite low, less than 0.5. Right? But whereas in summers when it was not too hot, like the temperature was less than way less than 40 degrees Celsius, the probability was quite high. That's why you see a like a larger circle. Similar is the case with monsoon as well, right? I think even in monsoon, if there is like high temperature, I don't think there will be any high temperature. But here in this case, if we somehow categorize a temperature to be sunny in this monsoon season, people did play. There is like this a bit of coolness on top of it, sunny weather. Similar is the case with the winter as well. So there is like hardly any case where it will be too sunny. So it was like bearable. So when I say sunny, it is like the outlook, not in terms of the temperature as such. You can see outside and see there is sun out. So that's what we call sunny here, right? So in winter, if there is sun, it's like really pleasant. Same is the case with monsoon, but not the case with summer. So this is a sort of typical case, one of the cases. And let's look at this case as well, something very similar. I think this is like highlighted here. And in the other case, where it is windy, right? So there is like this strong blow of air flowing from some direction. So your football is like difficult to control, and you also find difficult to run in the field. So in the case when it is summer and there is a strong wind, you can definitely see there is this high probability of the match being played or not, whether you want to play the football or not. But in the previous case, the probabilities here was like when it was sunny, the probabilities were quite low. In the case here on the when it is like windy in the summers, I think it is not a problem. People were able to play. That's why the probability of playing is quite high in this. The circle is quite big. At the same time, when it is monsoon, and even if there is no wind, you can see the probability is quite high, but the probability goes like quite low when there is a strong wind. So we can get to know that in some monsoon, the wind is like quite strong compared to the summers, right? So that's why this contrasting difference in the probability of play. Similar is the case with the winters, but I think the winter also doesn't have much strong winds. So we were still able to like play. That's why you see the probability like quite high. Okay. So what if I want to combine these two things together, sunny as well as windy, the combinations which comes out from sunny and windy. So even for that, we are given some data set. So the data that we right now have got contains in one column something that we call outlook, right? And that outlook has like various values to it. And we have some places where it is sunny and windy. There are some places when it is sunny but not so windy, and so on, different combinations. With those combinations, we have recorded whether the match was played or not, and from that we calculated these probabilities like these, right? So we want to put all these ideas in a more formal way, right? And what is really happening here is when you have one attribute with you, let's say sunny here, right? And we augment that attribute's information with one more attribute, let's say called windy here, right? So which means by knowing a particular value of an attribute, there is a certain difference in the probabilities. So for instance here, if I say a particular weather condition where it was not sunny and there was wind, the probability is quite high, right? But if I like contrast this to the other case, when in the same summers I don't know any information about wind, but all I know is it was sunny. So the probability of playing that particular game of football was quite low. But the moment there is one more information added, like there is no sun and there is wind, the probability kind of slightly starts to change. It drifts in some different way. Like you can see here, the sun is like there is no sun and the wind is like present. The probabilities are like quite high that the match will be played. So Naive tries to understand such interaction. So given a data set of whether a match was played along with many attributes of the weather condition, a prior knowledge of a particular attributes does influence your probabilities, right? The probability can either go down or go up. So formally putting this entire idea into a very elegant formulation, which is called Bayes theorem, which puts in all of these information in one neat form. So in order to explain this in better terms, if I want to understand a probability of whether a match will be played or not, that's represented by this symbol called C. So this is something that we call class, right? And the class is either the match is going to be played or not. And that's kind of also relates to the thing which we discussed around classification problems, right? And if I want to calculate this probability, which we call posterior probability, which is whether the match going to be played or not, given I have all these attributes with me. The attributes like whether it is sunny or not, whether it is windy or not, and so on, right? And on the right hand side, this Bayes theorem puts things pretty elegantly. On the numerator, you see something called likelihood, right? So if I say what is the probability of the match like to be played today, given I have these sort of weather conditions. So let's particularly take given it is summer, right? In the likelihood, I might have the other information with me. What is the probability of the particular weather to be or the weather condition to be summer given I am kind of able to play here. So in order to show you some calculation on this, let's discuss about this frequency table, which will then translate to the formulation of that Bayes theorem. So here, this frequency table tries to captures certain information in our data. So the first information is when it is sunny. So there are like two possible cases here, yes or no, it is sunny or it is not. And on the column, we have whether the match was played or not. So in total, if you count all these 3 plus 4 plus 1 plus 6, there are 14 observations from the historical data we have got. And out of these 14 observations, there were 3 times when the weather was sunny and the match was played, right? But in contrast to this, there were 4 instances when it was sunny and the match was not played. So obviously the other side is has a high probability than the yes ones. And similarly, when the match was not played, the weather was not sunny, there were 6 instances when the match was actually played. So which is like a strong indication versus this one here, which means when the outlook is not too hot, not too sunny, the match was like most of the time played, right? So I can do the same for windy as well. And the other variable that we have is the season. So when it was summer, I could say the chances are like equally likely for the match to be played or not played. But when it was monsoon, interestingly, there was no match got cancelled, so every match was played. And in winter also, the chances are like equally likely whether the match was played or not. So with this sort of frequency table, it's easy for us to now visualize what is the sort of probabilities associated with each of these cases of having a wind, or if it is going to be sunny or not, or even having the information about the season of the play, right? So this frequency table we're going to likewise extend, and we're going to come out with something called a likelihood table. So these are counts, right? Frequencies, what we call. So with these frequencies, we can translate this to a likelihood table which consists of different probability measures, right? I'm going to explain how this is calculated. So for instance, let's take the variable season, right? We can do this for the other 2 variables as well. So the one which we are going to take here is for seasons. And what we have got here is like this. You have a match either played or not, So if I like count all the matches which were played, which is this column, irrespective of which season it is. So that's 3 plus 4 plus 2 here, right? There were like total 9 matches which was played out of the 14 observations given to us. And then there are these 2 plus 4, so 2 plus 3, which is 5 matches or plays where like it was not played, irrespective of which season it was. So if I want to translate this to a likelihood table, all I need to do is, as you know, to translate such a frequency into a probability measure, in the denominator we have the total possible outcomes, and in the numerator the outcomes which favors our event, and our event here is whether the match was played or not. So there were like 3 instances when the match was played, divided by the total 9 instances of the match was played in overall. So these 3 instances belongs to the season summer, right? So there were 3 times when the match was played out of all the matches being played in the observations which was given to us. So 3 by 9 is in particularly the score for saying the probability of the season being summer given the match was played, right? So this symbol that you see here, the pipe kind of symbol, it is read as given. Probability of the season being summer given the match was played. So this can be calculated pretty easily like this, 0.33. And this is what our likelihoods are. So if I like go back a couple of slides here and tell you this particular Bayes theorem. So this portion in the numerator is what we called likelihood, right? And this information is known to us. And what we are really interested in calculating is this posterior probability, which is going to come up after we collect all the data points. Okay, so the next one, the portion which is like the probability of a particular season to be summer, or the probability of our class, which is nothing but whether the match is going to be played or not, is what we call the prior probabilities. We know that, right, from the data. So in this case, there were 5 observations when the kind of attribute value is the attribute seasons value is summer. So we are able to get the probability by this 5 by 14. And remember, these are class probabilities. So the 14 in the denominator is because of the fact that we have 14 observations collected from all these matches. So which is 0.36 here. And similarly, here in this probability of the class, which is whether the match will be played or not, it is an overall level. So 9 by 14 is that probability. So this is the probability of your attribute, which is the season, and this is the probability of your class, which is whether the match will be played or not. And both of these probabilities are something that we know by the name of prior probabilities. These are known in prior, even before we do the sort of calculation from the data that obviously from all of these are coming from the data we have. So if we put all of these into our Bayes theorem, this is what we get. The likelihood multiplied by the probability of your class, and in the denominator you have the prior probability of your attribute, which is nothing but the attribute season here. And in particular, the value which you get is for the summer season. So this becomes in very short form the likelihood, the probability of the match being played given the season here is summer. So similarly, if we do this for all the other attributes as well, so the X that we have chosen at this point is only for the season, right? But I can do it for the other attributes as well, which we have got. The other attributes like the sunny, which is yes or no, or the windy, which is again yes or no. So if I put all of these together, like in this form, the probability of winter given yes, the probability of summer is equal to no given yes, and for the rest of the attributes as well. So remember, all of these are attributes and it has like taking a specific value. So in this case, I'm trying to calculate the probability of the match being played, and there are in total 3 attributes. So that's why you see here the value of season being winter, the value of the attribute sunning being no, and the value of the attribute windy being yes. And this is the prior probability of the class. So in overall, this is a probability of whether the match will be played or not, given all these attributes. In the denominator, likewise, we get the prior probabilities of our attributes, which is the season, sunny, and the windy. These are the three attributes. Right. If you put all these values inside this probability, this is what we get. The probability of the match being played given the season is winter, it is not sunny, and it is windy. Right. These are the attributes we have got, and the probability is 0.6223. Similarly, if I want to get the other side of the story, I would simply, because there are only two classes, I can simply do 1 minus of 0.6223, which will give me the probability of the match not being played, which is obviously less than this. So in very simple terms, like you can see that we have only come out with probability here, right? So where is this classification that we were initially talking about? And in very general terms, people normally fix a threshold of 0.5. So if I see the probability of the match being played greater than 0.5, I can say my decision here would be to play, right? No otherwise. So this threshold can be changed also. In typical all the cases, these probabilities are fixed at a level of 0.5. Anything which is greater than that, we accept that. Anything below the probability is like not accepted. All right, yes, so I'm happy. We can play the match. Right. So this was a very simple dummy example. So let's build a really strong use case on this with respect to a real world problem. Right. And these are some typical examples that you can see. Face recognition, detecting email spams, and even categorizing the news. All the places where you can have some sort of classification algorithm, you can do that. You can use naive-Bayes. And like a typical picture from the Oscars, and you can see there are like all happy sentiments. So this is like another step also that you can do, which is again a classification type of a problem, whether the expressions in the faces are positive, negative, or neutral. Right? Okay. Some more examples, medical diagnosis. So for example, if you are given a medical history of a patient, you can also classify whether the patient is going to be soon diagnosed with that disease or not. So for example, diabetes. If I have all the readings or like all the medical tests for diabetes of a particular patient, I can classify the patient that he or she going to be diagnosed with diabetes in 1 month's time. Right? These are again a classification problem. Once again, digit recognition. So if you have a handwriting data set which is of the numbers 0 to 1, and somebody has written this, so these are like different ways of writing 0, 1, 2, and so on. So given this as an input, can I learn this data and classify, given another new data set to me, can I classify the digits either into 0, 1, 2, or 9? Like these are the numbers that I want to classify my data into. Can I like do that? Yes. So this is again a typical classification problem example. So I'm not saying that for all these problems, naive-Bayes will be the best algorithm to do, but naive-Bayes can also be one of the algorithms which can be used for classifying, right? But obviously, machine learning is also about experimenting with all these sort of algorithms we have got, and all these algorithms that comes under classification, that solves the classification problem, has its own benefits. So you should be better informed in terms of doing many sort of different experiments with your data and then figure out which one does the best. Okay. So we're going to take this one real world example of predicting employees' salaries, right? So a typical use case could be if you are a marketing agency, right? Or let's say some firm who is analyzing salaries of the employees, right? From various firms and from various backgrounds and so on. So there are hundreds of things which decides the salary of a person, right? So if you have your hands on certain information from a market survey or from employees survey across companies, you might be able to get some picture out of it. And let's say you decide as a marketing agency, such kind of reports are being produced, and many HR analytics companies does this as well, where they analyze the current market trends and they try to come out with predictive models around that. Right? And the predictive models could be given some skill sets that you have, what is the expected salary that you might draw from job that this skill set will give you. So there are many such predictive analytics kind of use cases, which is quite common in the HR analytics. So let's see if we have some data of the employee. Can we predict exactly what is going to be the salary? So there are like two ways this problem can go in. One way where we can think of this as a regression problem, which means very precisely predicting the value of the salary, or this can also be categorized. Like if I'm saying anything greater than $50,000, $50,000 is a high salary, and anything below $50,000 is a low salary. So the two classes in which I want to predict or like put my employees into will be either low or high. Keep in mind that this prediction algorithm I'm not building for my own set of employees. If I'm running a company, I'm not building it for my employees. I know their salaries, right? This might be the case for some HR analytics company who is in general wants to understand what's the trend like of. So if I show you this data, this is what typically it contains. It has information like age of the employee, what is the type of the employee, some information on the education, like education definitely plays a big role in deciding your salaries. And then general informations like the marital status, or whether the employee has any sort of relationship or a family, right? And even the race of the employee. So whether all of these are important or not is a matter of continuous experimentation, but these are the sort of information we have of any employee in our database, right? So if this HR analytics company wants to do something with this, they might be able to use all of these fields. There are like even some of the variables like capital gain, sort of very rare to find for a particular employee, but yep, this data set has it. So which is typically the income from the various investment sources the person has, the employee has, right? Other than obviously the salary. Okay. So if I have this data set, I think there are certain variables which are very clearly telling me are useful, and there are certain variables which I believe can be removed. So let's maybe get rid of some of the information like the marital status or the employee's relationship status or the race of the employee or gender, capital gain and capital loss. So there are like certain biases as well in this particular removal of the fields. There are certain strong assumptions, but I'm not anyway getting into those sort of debates and discussions which quite happens in the industries regularly, particularly with attributes like race and gender, right? But I'm not going to go into those discussions. But for a very safe assumption, let's assume that a fair play kind of an environment in industry would normally don't want to use any of these variables, right? So we have a question here which says, how does one decide which variables to use, right? Pretty common question here. So the first judgment that anybody do on which variables are important is based on domain, right? So, for me to remove these fields from the data point, there is a particular emphasis given on the meaning of these variables. So as an HR person might be able to see these variables and straight away reject that we should not be basing the employee's salary based on these variables. Like doesn't matter if the employee is married, unmarried, or not in a relationship, or the employees of one race or a particular gender and so on. These should not be taken into consideration, keeping in ethics in mind, keeping in the industry standards in mind, and giving a fair play for everybody to get an equal opportunity. So if I like consider in those lines or talk in those lines, domain knowledge helps us to see which variables are important and not. So that's first. And if you have a like enormous amount of variables with you, maybe let's say in millions term. So if I'm doing an image classification, in image classification the pixel values are like many, right? And I can create a large matrix of data points, numeric data points. So there are traditional methods like principal component analysis and many dimensionality reduction approaches, which helps you to represent a large data set, right, which contains many columns in a lower dimension. So when I say lower dimension, if you have a data set of 1,000 columns, can I represent this 1,000 columns in 10 columns, right? So this is called dimensionality reduction. And the way we do this normally is these 10 columns are a representative of all the 1,000 columns we had in the beginning, right? Some linear combination of the 1,000 columns. And there are like standard techniques, if you would like to go and read more about it, called one of the very popular one is called principal component analysis, which helps us in doing this dimensionality reduction. So in short, there are two ways to do that. One is domain knowledge. The second is some statistical methods or mathematical methods like PCA. All right. Okay. So now let's prepare this data for training our model. So a typical machine learning process flow of coming out with a model, the first thing that we do is to divide the data set into two parts, right? The one which is used for training, and we will like reserve a portion of the data set for validating or what we call testing. So imagine like this, you build your model on, if let's say if you have 10,000 observations with you, 10,000 rows of employees, you use, let's assume 70% of that data, maybe something like 7,000 data points. So out for these, and which are like obviously randomly selected. So out of these 10,000, 7,000 employees you choose and train your model. And when you're done with your model, you need to also see how good is this model in terms of deploying it in real world. So I'm going to reserve these 3,000 data points for the later point of time, where I will evaluate the goodness of this model, right? So I'm going to describe that a bit more when we are going to see the demonstration. This is like a standard flow that I'm walking you through first, right? So once we divide this, the next immediate step that we might have is obviously to build the model, right? So here we are going to use a particular function coming from our library. I'm going to describe that during the demonstration and build our model, right? And then comes the other step. After we are done with the model building, we are going to see the output and see if the output is like good or bad or like in whichever way it is. And then we'll also see what we call the evaluation. Once we are done with the model building exercise, we should be able to find out if my standard metrics on which I evaluate the models, does that tell me everything is good and I can like proceed with this model being deployed in a real world, or like something I need to do about improving the accuracies, right? I'm going to talk about that as well. So there are certain standard ways we can improve, like including Laplace correction or doing some normalization. So I might not focus on that part, but I'll be focusing on building this model first and trying to understand the various accuracy measures, right? And then comes the model validation, which is again based on our test data set, right? Which we reserved in the beginning. Okay. So we're going to discuss about the confusion matrix. What do you mean by sensitivity, specificity, and all that different measures that it gives me. And obviously, if everything goes well, we say that the model has some very good accuracy and we can trust on this model, maybe at least 80% of the time, or maybe 90% of the time, depending on what is the accuracy. And the most important or the most sought out sort of the step in this entire model building process is the prediction, where we are like actually looking at a new data set and saying, yes, this is what the predictions are, right? So these are the typical steps involved, starting from data acquisition to predicting the values from the model that we have built. So now I'm going to get to a demonstration in R. So I have here some data points, right? So this is a data set on the employees data we just now looked at. I'm going to show you how this data is like. Let's get the column names. So these are the columns that we saw in the presentation, right? So age of the employee type, education, and so on, right? And as I told you in the beginning, when we are building this model, there are two ways we can build this model, as a regression problem or as a classification problem. So we decide to build this as a classification problem because we are using Naibase. And in order to do that, I'm going to convert this employee salary into a categorical variable by saying a condition. Wherever in the employee salary variable I have a value of like greater than 50K, I'm going to mark that as high, and the rest of it are going to be low, like only two class problem, right? So that's why I'm using a if else here. So let's create this new variable which is called SAL and attach this to our main data frame. So now if I show you the data frame or the data set, this is how it looks like. The age of the employee and all that details, followed by the last two columns where we have converted or like written this particular value, which is, so here we don't have a crisp value, Here we have a value which says the salary is less than 50K, and this is like a good ethical practice as well. When you get a salary of some person, always anonymize it, or always like transform it in a way so that the exact values are not known. So if it is less than 50,000 K, I don't know whether it is 1,000, 2,000, 40,000 or like 50,000. It's just a range. And in the last column, we have the variable that we just created by using these values. Okay. So let me like just get rid of, there are 16 variables here. So I'm going to get rid of the one column that we just transformed into something else. So the column which was saying less than 50K and all that, it is removed, and I will keep only one column here, which is the low and high, right? So this is the sort of data set on which I want to train my model. And remember, in the classification problem, the training happens with respect to the class. So when I read this one row, it tells me if you are working for a state government and you have a bachelor's degree with you, so it's not too high, you don't have a master's, you don't have a PhD, like let me ignore these variables like marital status and all, and there are some capital gain values, also the number of work hours in week that you are like working for. So if you have like these values, it seems like the salaries are not so high for that. But maybe if I look at some cases where the salary is high, what is the sort of difference here? I'm just simply exploring the data to generate some intuition for myself. Like, and this is typically happens in every other data set also that you analyze. You need to create a intuition first before you start to build the model. So in this record where I can see a person is working for a private, maybe a private job, maybe it could be an industry company, he or she has a master's and like some more information, and it seems like the salary is high. So I think some indication here saying if you have a really good degree with you, which is at least at a master's level, there are like good chances you will be paid high, right? At least one inference which I can get. But anyway, we are going to use many of these variables to build our model here. So this is like just one variable that I'll explore and understood something about it. Okay, so now let's do this sort of splitting the data into two parts. So in the slide we talked about this process, right? We are given a data set. I want to preserve a set of observations for the final validation part, right? So to build my data set here, to build my training algorithm here, I am using a function called sample, which simply takes in all the observations I have got here. The number of data points that I have is 1,000 observations. So there are 1,000 employees data that I have got. So I'm going to randomly select some 70% of these employees to be part of my training data, right? How I am going to do that is to use by using a function called sample, which is randomly selects the records based on a probability, right? And the probability says here, like there are two values to this probability, which is 0.7 and 0.3. So what it means is there is a 70% of the times you want to select 1, and 30% of the time you should select 2 or any other value. So what this means here in the top first, let me separately run this for you and things will be clear. So if I take this example here and if I run this particularly, you can see that it will generate lots of 1s and 2s, right? What it has done? It has done by taking this input which says in the range of 1 to 2, generate me many such integers like either 1 or 2. I could also have like written 1 to 10, then it will generate 10 random numbers. So for instance, if I do sample of 1 to 10 without specifying any other parameter, it will give me 10 random numbers between 1 to 10, right? So here I'm saying generate only between 1 to 2 and do it like as many a number of times as you have in my rows. So what I am doing here is in my data set, we have 1,000 rows, right? So n rows give me 1,000 as a number there. And I'm going to generate between 1 to 2, 1,000 times these values like 1 or 2. And the probability to do that is being assigned as 0.7 and 0.3, which means 70% of the time generate me 1 and 30% of the times give me 2. So all I have to do then finally is, based on in which index I have 1 or 2, I'm going to go to my data set and say wherever this sampling function has generated 1, assign that to emp train as my data frame name. So let me run this, and then this, and then this. Right. If I look at now the number of rows in my emp train data, right, you see here 688, like pretty good number here in terms of what we were initially trying to do. So very close to 700, right? Because these are probabilities, you will not find exactly 70%, but very close to that. So if I do the same with test, you see here 300 types. So that's how the sampling works. So you can change these probabilities, and based on that it will maybe generate some other proportion as well. Okay, so I'm done here with splitting the file or splitting the observations into two parts. So all I have to do is simply use the library or package called E1071, quite useful package. It has many machine learning models implemented in it, and one of these machine learning models is Naibase, and also the caret function, which I might be using for drawing the final evaluation matrix, which I'm going to discuss in a while. So here what I'm saying is there is like a formula type of interface to this function, which means this is my data, right, called emp train. We know that we have split that in the earlier step, and what it says is use all the attributes given in my data set to generate this model and train it on the variable sal, which is nothing but high or low, right? So putting this dot here means use all the independent variables. An alternative to this could also be like I am selecting a particular variable. So for instance, so I'm going to select a particular, I can run this model and this will be like perfectly fine, but because we decided to run this model for only certain variables, so what I'm going to do is I'm going to print out all the column names of the employee training data. So I'm going to select all these and only keep the one which I am interested in. So let's say age is an important one. Okay, so we'll keep age. Employee type also seems to be important. We'll keep that as well. The serial number might not be required. Education, like very important, I'm going to keep that. Let's say education category also will keep. We are not interested in marital status, but we'll keep the occupation right here. And the relationship of the employees are also not important. Race is also not important. And let's also take out the capital gain and all these values and keep the working hour in weeks and the country of residence, right? So what I'm doing here is I am like simply adding this plus symbol. Don't worry, this is not literal addition. In this interface, in this particular model function like Naibase, the plus simply means the combination of all these variables. Like these are the variables that I'm going to use to build the Naibase model, and it is going to learn basis the label, which is high or low. Right, seems good. So let's run this model. Okay, that's quite fast because of the small number of observations we have. Let's put the summary of this entire model. Okay, so like that's quite a big summary. Okay, let me read some of these for you so that you can understand what it is doing. These are actually the likelihood tables. You remember we in the slide we were like finding out what was the frequency table and the likelihood table. So in this case, all of these values that is being printed out in these after this particular header, which is conditional probabilities, all these are likelihoods. And the one which is this one is the a priori probabilities, or like simply saying prior probabilities of the class. You remember the class has only two values, low and high. And this says that 76% of your employees are low, having a low salary. So that's our prior probability, right? In the given data set of ours, 76% of our employees has low salary, and the rest is 0.23. And this, the one which is like starting from conditional probability, is all the likelihood tables for each of the attributes, right? So let me tell you how to read this. In the first case, we have this attribute called age of the employee, right? It says the first column here, there is a small matrix here, right? So this means because age of the employee is a numerical value. So for numerical values, like calculating the probabilities is not like possible. So what we instead do is we calculate the mean and a standard deviation. So what it means is, if I read this value, on an average, employees who have a age of 43 or like 44 years has the class in high salary, which is like making sense also for me, right? Because as you grow in age, you become like more experienced in your domain and you start to draw high salary. Whereas the average age for people who are earning low salary is 36 years, right? So these are averages, keep in mind. And because I'm putting here the averages, I should also be talking about the standard deviation. So that's what is given in the second column. And standard deviation, as you might know, gives us the understanding of how much variability is present in the data. And here the variability is like in terms of the age itself, which in terms means if I have the average of high earning employees, the average age of those employees are 43.9, I can say plus or minus 9.8. That's the sort of range, right? So there are many cases where you will see the variabilities are quite high. Even young aged employees are earning very high because of their background in terms of academics or something else, right? Maybe they are family wise pretty good and some many other reasons. So there is always a variability in the data. So it's important when you talk about averages, you also include the standard deviation there. Similarly is the case with the low category as well, low salary category employees. Okay, so this same conditional probability table kind of changes in its tone when we have a categorical variable like the employee status type, like employee state type. So here we have the states like the employee works for federal government or local government or has never worked, works for private, self-employed, and so on. Like there are many, or like without pay. So these are the probabilities associated with these conditional probabilities. And if you remember, the way to read this is the probability of the employee working for federal government and he's like earning high salary, right? These are conditional probabilities. So remember that. So if I like give you some contrasting examples, maybe this will be easy to understand then. Most of it are like very close. But if I maybe take this one, where I can see the probability of employee working for federal government, the salary being high has like a higher probability than the salary being low. But whereas the same thing in private sector, like the probabilities are very close. So maybe both these type of people are there, high salaried and the low salaried people. So this gives me an indication rather like what decides a high salary. Maybe I can think of this in better terms if I see the education. So if this is my education like 10th grade, 11th grade till masters or doctors as well, you can see the stark difference in the probability measures. People who have a doctorate degree, the probability, the conditional probability there of having a high salary is like quite high compared to a doctorate candidate like getting a very low salary there. So this difference is quite distinct. The moment I see this, I can like definitely say having a higher degree like give us this indication that the salaries are also going to be high, but there would be definitely exceptions. Like, so this is how you read this model. And then finally, there are like many more other columns as well. So this is the sort of summary of the model, but the one which I am interested in is what is the prediction? Is this a really good one or a bad one? Right? So that's what we want to understand. So remember here, the prediction I am not going to do on the training dataset, though we also look at the training dataset predictions as well. But in particular here, I am looking at the testing dataset prediction. So let me run this. Okay. So I'm using a function called predict. The model name is emp_nb, which we created here. And I'm giving now a new data set to this predict function, right? Which is the testing data, which we initially reserved for the accuracy computation and all that. So let me, I've run this. So I'm going to now evaluate how good my model is by drawing something called confusion matrix. Let me give you what it is. Okay. All right. Not bad at all. I think the accuracy is quite good. 83.01%. So that simply means if I take this matrix of high and low, like look at this particular table, a small table, right? So the way to read that is, in your original data set, the values for high and the prediction that you have done exactly matches. So which means the 48 here are the number of employees, the 48 are the number of records or employees who has the high salary in the actual data set, and your model also predicts the same, right? Similarly, these 211 observations, your actual data contained the value low and your model also predicts the same. Whereas these are the wrong predictions, the 30 and the 23 here. So what it means, your predictions are here maybe high, but whereas in the actual data the predictions are low, and the vice versa for this one as well. So the off diagonal elements are something which is not good for me. That's the sort of error. So how this 83.01 is calculated? If I look at this, out of how many? Out of let me like sum this first. What is the total number of observations? 48 plus 30 plus 23 plus 211. 312. Like this is the number we saw for the testing data set that we created at the beginning. So the accuracy here is based on the diagonal elements. So that means 48 plus 211 are the correct predictions. And the total observations that I have is 312. And here you go. So this is the accuracy measure that you have got, which is like 83% here. Right. And there are some more information as well in this sort of output, like confidence interval. So when I'm putting accuracies, it is also possible for me to calculate like if this accuracy that I am talking about is going to be having certain marginal errors, right? So when I say confidence interval, my confidence interval of 95%, which means I am 95% confident that the accuracies are going to be somewhere between 0.78 to somewhere between 0.87. For this instance of data, I am able to only get 83. But in general, if you do draw many samples from this given data set of mine, I can calculate something called confidence interval, and this confidence interval can have different percentages, right? So there is only 5% chances that my accuracy will lie beyond the boundary which is mentioned here, right? I cannot like get, there are only 5% chances that I can get an accuracy of more than 87%. And the same for the boundary which is less than that, which is less than 78%. So at least 78% of the accuracy I'm going to anyway get 95% of the times, right? That's what this gives you. And then comes certain things like p-value, quite popular measure. If this p-value is less than 0.05, things are good. That means the sort of here accuracy is very well coming out for the data. And if it is greater than 0.05, it is not that good, right? And there is some more stats here, some more evaluation metrics I should call, like the kappa statistic, right? So this statistics is quite interesting if I want to talk about it for a while. There is always a process that you can follow. So this is your accuracy which you have got from the predicted model, right? But what if I create a very simple model which says by doing a random selection? For example, I have only two classes possible here, either high or low. So what if I do a simple tossing of a coin, and if there comes a head, I'll say the employee's predicted salary is high. If there comes a tail, the otherwise, right? So if you do this tossing of coin, you know that 50% of the time you are going to get head and 50% of the time you are going to get tail. So that means my accuracy of the model, even if I do this brute force or like simple naive approach, I am going to get a 50% accuracy. Or even if I like call a chimp and ask the chimp to select either a high or low, the chances are that the model that is created by the chimp is going to be 50% accurate, right? So how good is my accuracy with respect to that accuracy of a random sort of a process or a model that is created by a chimp, right? That's what is like given by this kappa statistics. And if you like want to understand how that works, you can like see here, this is your total accuracy, and this is the sort of accuracy that you get from a random stuff, right? So if this difference in the numerator is not going to be low, if it is going to be low, that means the kappa stats is not like very good, and that can only happen only when your random accuracy and the total accuracy are very close to each other. But more this difference, higher will be the value of your kappa statistic, and the better the model, right? This is how it works. And then there are these variables like sensitivity and specificity. I'll talk about this for a while. So how these two important measures are like considered normally is, in any model that you build keeping a real world context in mind, you have to always make sure that both your wrong classification, like when there is a employee who has high salary in the actual data but you are predicting to be low, and the other case, both of these wrong prediction cases needs to be balanced. I'll tell you why it is important. For instance, if you are building a model for a healthcare data set, wherein the task that is given to you is to predict whether the patient is going to be diagnosed with diabetes or not, right? So now imagine what wrong can happen if you predict a person who is completely healthy, but your model predicts that this person is going to be getting diagnosed with diabetes, or maybe some even more dangerous diseases like cancer. So in that case, kind of agony you're going to put to that patient because your model has done that, it's going to be like really risky business for you. The other case is also not good, right? Whether when your patient is actually going to be diagnosed with a particular disease, but your model says that's not the case. So if you want to give or attach this to a monetary value, let's say you do this for a banking system. The same model can also be built for a bank, right? Where a given transaction needs to be identified as a fraudulent transaction or a genuine transaction. If a fraudulent transaction is tagged as a genuine transaction, you are like going to lose a lot of money there. The other way around is also not good. So sensitivity and specificity particularly handles these two scenarios well, right? If you are able to achieve a balance between sensitivity and specificity, at the same time keeping the accuracy also intact, then you can be certain that your model is completely fine or completely good, right? But if there is not a good balance between sensitivity and specificity, then that means in either one direction your model is like highly skewed, which is like a danger point to be in, right? So keep a balance of the sensitivity specificity, and here I can see that it's not so different in terms of its values. At the same time, I can see the accuracies are not bad at all. So 83% is like quite good number, right? So I think the one thing which we have not seen is what is like the final prediction looks like. So this is how it looks like, right? So highs or low. But instead, if you want to, let's say, because naive Bayes is about probabilities, I can also get you the probability score instead of getting the class name. So if I use the argument called type equal to raw, you will see that the output of this prediction is actually probability measures. So how to read this? Instead of class, this is like the probability of this employee having a high salary is like 0.7106 versus the probability of the employee getting a low salary is 0.28. So whichever is like higher, you can take your classification in that direction. All right, so that's it from me on this naive Bayes algorithm. Thanks for listening.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!